Hi, I'm Max Clark. As a network engineer, one of the gremlins that we constantly chase is asymmetric routing. It does all sorts of stuff to you. It makes it really hard to troubleshoot, and it just turns into a nightmare really quickly. And what I mean by asymmetric routing is path one way is different from the path on the return, right? So if you have a network between Los Angeles and New York, and bandwidth and traffic going from LA to New York goes the southern route, right? So LA, San Diego, Phoenix, Dallas, Georgia, and then up the seaboard, right, to New York. And on the return path, it takes a northern route. So, New York, Pennsylvania, Chicago, Denver, San Francisco back down, right? Let's say you're doing that. When you get into these scenarios, you get into things that we would call like just strange things happening, or things just don't work right, or, performance is just weird, or, it's just a nightmare. It is an absolute nightmare to troubleshoot. So you spend a lot of your time trying to prevent asymmetric routing because you want predictability in the path on the egress and the ingress. So that way you know what's going on. You know what network interfaces you're traversing. You can identify what routers you're on. You can control it. Just makes it much better to troubleshoot. You can identify problems much faster, and you can route around them much faster. About 20 years ago, I learned that asymmetric routing can be your friend. When you know the rule, you know how to break it, or when you can break it. And the first time that I really understood when and how to break the rule with asymmetric routing was with load balancers. And when the first load balancers came out, the first on the market were really proxy servers that could do traffic distribution. And then you had load balancers that were, using routing to make traffic, decisions. And the load balancer still has to rewrite the source IP address information when it passes to an application server. But if you just think of it from top to bottom, right, traffic would come in, hit the first box. This is the load balancer. The load balancer would say, okay, the next box it needs to go to is here, and it could select which server to send traffic to. And that server would then see, here's a source, and my default gateway is the load balancer, and I know how to pass it back, right? And so you could have a routed-based load balancer, or you could do a source NAT. So the server would know, okay, this is the device I need to send traffic back to, and then that load balancer can send traffic back, right? So either doing again, a source NAT, or you're doing some sort of layer 3 router with a gateway, default gateway on this server, so that way traffic flew back and forth. What was nice about this setup is you actually knew exactly how much traffic was flowing through the load balancer, and the load balancer could keep really close track on session capacity and application performance and traffic flowing back from the server back to the client. Now, of course, the disadvantage of this is everything's flowing through the load balancer. And that means that as you size up and scale up your traffic and your traffic to your servers, your load balancers become really critical points of failure in the path, and they also become very expensive devices because they have to support all of the traffic that flows through them. So about 20 years ago, and the first ones I was aware of that did this was Foundry Networks, and they came out with their Server Iron product. And the Server Iron had a ability to do direct server return. We also refer to this as like one-armed load balancing, or you hear like things like three-legged configuration in your load balancer. But really, the technique and the terminology with the Server Iron was direct server return. And the way this was implemented was, router device up here, virtual IP on the load balancer. So this would become your IP address that you were using to publish to the internet, or that was published through your firewall. So it would come in, hit the load balancer, and the load balancer then had a pool of application servers. And the load balancer would say, okay, whatever the load balancing metric was that you were using, round robin, although most commonly you're using like at least connections, right? You wanted to send traffic to the server that was being used the least. So you would send from the load balancer would say, okay, we would have, server 3, send traffic to server 3. Now, the tweak that direct server return required was the server now is seeing traffic going to it destined to the virtual IP on the load balancer, and the server wouldn't know what to do with it. And you would just bind an IP address to the loopback interface of the server that was the virtual IP. So that way when the load balancer redirected that traffic to the server would see it destined to itself in the loopback interface, would be able to respond to it. And now here was the fun. The fun thing was that the source IP address wasn't the load balancer. The source IP address was the client. So the server wouldn't respond back to the load balancer. The server goes straight back out. So now you have this triangle that's flowing. Disadvantage of this, of course, is that the load balancer doesn't see traffic flowing back from the server to the internet. It only sees one way. So it could not tell if there was a application problem on the server, if the server is responding slowly. So you'd have to implement health checks in different ways to try to keep track of all this. But the positive of it was the load balancer is seeing far less traffic and resources through it. So an average content-heavy website, web platform was maybe like 10% egress, 90% egress. So for every 1 megabit of traffic that was flowing in, 10 megabit is flowing out. So now if you think about that in terms of sizing and scaling your load balancer, if you only need 10% of your overall traffic flowing through your load balancers can be much smaller and they can scale much more efficiently. And then we could do other fun things with them because they were only seeing one side of the traffic. We could then we could load balance the load balancers. So, on a network level, you could do this with ECMP, which is just on the router itself. You can create multiple routes within the router or the switch or whatever your gateway device is with equal cost pointing to different endpoints. And depending on the device you're using, maybe you could do it like 8 times. You could have 8, and it was really crude load balancing. But in a pinch, it worked great because now you could have 2 cheap load balancers distributing traffic across pools of servers, and then you could have 3 cheap load balancers, and you could have redundancy and failover between them. This is one of those areas that when you started doing it, if you look at your infrastructure cost, you'd say, okay, if you had to go out and buy a really big load balancer, right? So what were the big ones, right? F5 big IPs were like all the rage. Or you would have, what was popular back then? I have to think through the cobwebs here. It was big IPs. It was the Alteon 83 product. It became the 84s. Those were really, really popular. This is right around the time that the NetScalers were becoming popular. Phenomenal boxes. I mean, you could do stuff with a NetScaler that was just, you could manipulate a lot of network traffic. But now, let's just talk about it from a cost standpoint. If you were spending $100,000 on a NetScaler, you would spend maybe $5,000 on a device that could do DSR for you. From a overall efficiency of being able to build out that infrastructure and scale that infrastructure, how you allocate and spend money starts to matter significantly at scale. Right. So, you could say it on the low end, you've got a relatively small amount of infrastructure, and that load balancer might represent, 25% of your total budget for that POP. Or maybe you're on the other side where you're trying to scale it up and you start looking at replicating those load balancers. That gets really expensive as well. This also creates a situation where, projects get deferred because the cost of the project just gets too expensive. DSR 20 years ago was my entry point into understanding asymmetric routing and how to leverage it and take advantage of it and do fun things with it, right? So first example is load balancing. 2 other examples that were really seminal moments for me in my career in network design and really tweaking the network to take advantage and do fun things and create a lot of operating leverage for the business. Second example I'll share was 10, 15 years ago, and I had a customer who was an anti-piracy organization. And so it's actually probably more than that. I'm trying to think. Yeah, that's about right. 10, 15 years. And so if you were trying to prevent people from downloading and pirating content on BitTorrent, for instance, or if you were trying to find people, doing these sorts of things, you had a bunch of challenges that you had to overcome. And one of those challenges that you had to overcome was IP addresses. How did you actually acquire and simulate enough IP addresses that looked like residential consumer IP addresses? That way the anti-piracy measures couldn't catch you and find you. And what we did with this customer was we convinced them to go out, subscribe to and sign up for dial-up modems and take advantage of different dial-up ISPs to get residential allocated IP addresses. Now, the problem, of course, with this is as soon as you're on dial-up, now you're talking about an application that first has to get bound to a server, but also is limited. I mean, at the time, dial-up was 56K. So trying to be effective on the internet on a 56K dial-up modem isn't really effective. Well, again, here's the tweak. If you look at it from a network standpoint, an application, and what the application was doing, really small amount of ingress and a lot of egress. Sound familiar? It's just like the example of a content website, right? So what we did for them was we split the traffic from the inbound and the outbound, the ingress and the egress, and it was fun. This customer went out and we got a DS3, so a lot of dial-up connections. So DS3 is 648 channels. Oof. It's been a long time since I've done that math. I don't even know. 600 and something channels, let's just call it. So per DS3, 600 something channels. It's 600 IP addresses per DS3. It's more than that. It'll dawn on me. Comment to the notes. Tell me I'm wrong, because of course I don't remember it offhand. It's been a long time since I've done DS3s. So the DS3 could, on their application servers, they could send an instruction to the concentrator, have the concentrator file up with dial-up, connect to the dial-up ISP, acquire an IP address, So now inbound IP address getting bound to the application server. That application server then had and would overwrite its default gateway, so traffic dial up into server out to the internet. In this case, the out to the internet was multiple 10 gig paths with a lot of capacity. So their egress traffic and where the bulk of their content traffic was flowing all flew out, via these high capacity 10 gig links, and it worked wonderfully. It was awesome to watch. The modern version of this that we're doing is related to AWS and managing and attacking these really high cost centers within AWS for some customers. And if you look at your AWS bill, chances are you're spending a concentrated amount of money around compute. I mean, that's pretty obvious. It's compute, it's storage, it's managed services, and it's egress, it's data. Now, we can get into an argument around compute and managed services and, should you be on Dynamo versus Cycla or Cassandra, or should you be running Kinesis or Kafka, or, if we just look at it from a standpoint of a steady state application. So everybody wants to believe that they need infinite elasticity up and contraction down. The reality is your application is probably always running at basically the same amount of resources, day over day, hour over hour, month over month, week over week, whatever. And once you start looking at that and you say, okay, your application is predictable in terms of consumption load, how much compute does it need? And if you have a application that has a predictable amount of data traffic coming in and out, or if you're heavy egress, these become scenarios that AWS becomes very expensive. Okay, just to make this point in math, if you're serving 10 petabyte to the internet and you're doing it on list prices with AWS, it's costing you $500,000 a month. If you're getting a PPA from AWS at 2.5 cents per gig, or half price of what their published pricing is, you're spending $250,000 a month. If you take that and go to a bare metal infrastructure provider and do a flat rate network circuit, you're spending $2,000 a month. $500,000 a month, $250,000 a month on a PPA. This is the committed contract embedded with an EDP with Amazon, $2,000 a month, right? Yes, there's a lot of other factors that have to apply that have to work out perfectly in order for you to be able to do this. But, we're talking about saving $2.5 million a year just out of thin air, right? Making this change, just changing how your network flows, how your data flows out of your environment. Going through this exercise and talking about shifting compute out of EC2 or EKS into a bare metal infrastructure, challenges became perception. Can we do this? How do we run it? What happens if the data center goes down, if the bare metal goes down, if we need to scale it? We're used to our tools and our flow, yada, yada, yada. And so there became a really simple, solve for this. And again, here's the modern version of asymmetric routing. And the solve for it was to take and put bare metal into data centers in region with the AWS infrastructure. So, if you're in US East 1, right, that means you're in the Washington, D.C. region, aka Ashburn, Virginia, or Herndon, Virginia, and go out and get data center in that market. And, you overlay this based on where you are, right? It can be Ohio, right? So you can Chicago, you can be in the West Coast, right? You can be in London, you can be in Frankfurt, you can be in Amsterdam, you can be in Singapore, you can be in Hong Kong. I mean, figure out what region is and where you need to be and where your infrastructure is, and overlay that with bare metal. And I'm using bare metal as a term because you don't have to go out and co-locate and buy gear. You can just go out to bare metal. You'll save more money if you co-locate and you buy your own infrastructure, but it doesn't matter because you can get such a cost savings off of bare metal, and you can leverage it anyways that you can just do it with bare metal. So I'm just going to use the bare metal terminology. And again, we just take advantage of a tweak on how we serve traffic. Now, again, assuming that you're heavy egress and light ingress, well, actually, it doesn't even matter if you're light ingress, because guess what? Again, ingress to AWS is free, but it's a measure of your direct connect cost, right? So this works best if you can be light ingress versus a heavy, ratio light ingress to heavy egress. And the way this works is, here's your steps, right? So internet traffic to AWS could be WAF, could just be straight to an ALB, to direct connect, to bare metal, back out to the internet. Fun thing about doing this is you can use your tooling that you have in AWS. You can use Terraform, you can use CloudFormation to manage your bare metal infrastructure at the same time. We have customers that have taken and extended their ALBs into their bare metal nodes. So they're running Kubernetes on top of bare metal, and the Kubernetes containers actually are getting their load balancing from AWS. There's lots of ways of doing this tweak and looking at it for your infrastructure. Now, what we're seeing in terms of average cost reduction on bare metal over AWS is about 72%. So if you're spending $100,000 a month on AWS, you're going to spend $28,000 a month in bare metal. You're spending $1 million a month on AWS, you're going to spend, right, do the math, $280,000 a month in bare metal. The reason why this is important is, well, I mean, geez, let's talk about it. You're saving a metric boat ton of money here. And that differential means a bunch of different things, right? We start talking about what is your cost per revenue to run your cloud. If you're looking at it from a standpoint of saying, hey, we're spending 15% of cost of revenue on AWS. So we're making this much and we're spending 15% of it on AWS. You don't have to be a finance nerd to understand that if you can cut that cost in half, it makes a big difference for your business. It makes a huge difference for you in terms of what you price your service or your product to your customers are, what your competitive advantage is, what your efficiency is, what your margin is. You want to start talking about EBITDA, if you're trying to do a transaction. You want to start talking about gross margin efficiency, if you're looking for VC, if you're trying to take investors, you got to go through any metric you can imagine. Having a more efficient cost model and delivery of service is just better for the business. You will grow faster. You will be able to hire more people. You will be able to go out and be more competitive. You'll be able to dominate in your space. Any phrasing that you want to say. My job here is to help you get to that goal, right? I'm going to get completely sidetracked on this rant, but it's a very simplistic tweak of just taking advantage of the fact that in some cases it's good to have asymmetric routing because then you can do some fun things with them. And, again, I learned this originally 20 years ago with direct server return and load balancers inside of a data center. We took advantage of this in a big way with a customer. I mean, they had thousands of servers and they did this at a very large scale for anti-piracy. And of course, now the modern version of it is just taking advantage of bare metal and AWS and not doing wholesale migrations. I mean, this isn't about, I'm not an all or nothing guy, right? Like there's lots of middle ground here. Maybe the middle ground for you is keeping your AWS environment and keeping your Dynamo and keeping your Kinesis and keeping all these different things you want to keep inside of AWS because it is a big engineering lift and shift. But being able to move a segment of your compute and your data egress out of AWS into something that you have a much better cost model on, it's going to give you a pretty big advantage. Those are the kind of things that become really fun because when we can, again, right? If we can cut significant percentage points out of an operating budget for a business, that business can use that money to do other things with. And those things usually are around growth. And I love to see companies grow. It is a miserable conversation to help companies contract. I love helping companies grow. I'm X Clark. This is just a quick note on asymmetric routing and how you can take advantage of it. And hopefully this helps you.